Okay, so today we're gonna be talk about set theory and its limitations, and how this can be translated to the limitations of mathematics, and how there are some unprovable statements in mathematics which cannot be proved whatsoever. We don't know what statements these are. We just know their statements.
Oh,
Can you see my screen?
yes, your screen is visible.
Okay. Set theory. Set theory came
Mm-hmm.
about in now. Firstly, I want you to try guessing what set theory is.
Okay, I don't have like an idea, but I think set theory is like a theory about sets.
I mean, it's in the name.
I am genius.
So smart you are.
Okay, so set theory. So sets are like these. I don't know exactly. Groups of information, groups of data.
Uh, Set theory can be anything actually. A set can be anything. It could, but the main thing is it has to be a collection. A set
Right,
in modern mathematics. Uh, it's really important by the way. Set theory. So set theory today serves as the foundation for practically everything we know. You've heard of the
right.
axioms, right?
No.
So axioms are statements which are fundamentally true, and we use these statements to form other statements and use those statements to prove important things. For
Right,
example,
important.
the proof that the square root of 2 is the square root of n, for which n is not a square number, is irrational. That proof, it's based off the axioms.
Right.
Now, these axioms are like really, really basic statements, like you could see here.
Uh-huh.
Stuff which you could think of out of thin air, and you just know they're true.
I mean, it
Now
makes sense
these,
for them to be true.
huh?
It makes sense for them to be true.
Yeah, they
Right.
must be true. Now, if these
They are.
axioms
Okay, right.
topple, then these are the foundations, right? So everything else topples along with it. It's kind of like
Yeah, we
building
can't
a
solve like.
building.
Yeah,
It's like kind of building a
that
building. Like if you don't have the proper cement while when you're doing the foundations, the whole building's gonna collapse.
that's a good analogy. Yes.
But what is set theory? So
What
the
is it?
idea of set theory is an attempt to formalize the axioms.
Mm-hmm.
So until like the 19th, 20th century, the axioms were just like written pieces of information. And you know how it is with written pieces of information. You can have statements which there are miscommunications. What George
Yes.
Cantor, a mathematician, aimed to do was eliminate this and make an axiomatic system made out of sets. Now, set
Right.
can be anything. It just deals with a collection of objects. You can have sets
Mm-hmm.
of numbers, sets of integers, sets of natural numbers, sets containing other sets.
Oh, right. Yeah. So sets are basically like groups of data.
Yeah, sets are basically groups of data. You can consider it.
Right.
Now you can do like lots of things with set theory. You can add numbers, subtract numbers, do basically everything what you can already do. So you can understand the importance of set theory. I have a small
Mm-hmm.
exercise for you.
Let's see. Yeah.
Should the set of all sets contain itself?
Okay, that's a very philosophical question.
Not quite, it's a mathematical one.
So if like I have a set that has all the sets,
Hmm.
but then that set has to contain the set itself because it's a set,
Yes, but because it's
and
a
then
set of all
that set
sets,
has to contain the set itself again.
yeah, it's a self-referential set.
So I don't think it should contain itself,
Okay, why?
because if it contains itself, that kind of destroys the whole point of having other sets. Because we can just have a set containing a set containing a set containing a set
Yeah, yeah,
that
yeah,
contains all the sets.
but not quite. When I say the set of all sets, so this huge set, will contain everything: sets of real numbers, sets of natural numbers, sets of infinity, sets of countable infinity, sets of uncountable infinity, sets of
Wait,
sets
I,
of
I have a
balls,
doubt.
sets of pencils. Go ahead.
I think this will be infinite. This set will have infinite number of elements.
Yeah,
I'll tell
it
you
will
why.
have an infinite amount of elements.
Yeah, because if like let's say I start with three sets, and then I make a set that has like two of these, and then two of these, and then two of these, right? So then I get six sets. But then I can pair those sets together. So like
Exactly.
let's say I have the sets A, B, C,
Hmm.
right? And I create a set D that contains A and B.
Uh,
But now I can create a set E that contains D and A.
you
And now I
can't,
can create another.
but you can't create a set which contain. Yeah, that makes sense. That makes sense.
Right, so there will be like infinite number of sets because then I can then create a set F that contains, let's say, E and A.
Yeah, you can do that.
Yeah, so
Completely,
it just
that's
goes on.
completely fine. That's completely supported by set theory. Now
That is
the
so cool.
question is, should the set, but should it contain itself?
No.
Unfortunately, you're wrong. The set of all sets does contain itself, because mathematicians have been trying to answer that question for decades. Actually, it was only in around like 1950s or 60s. I don't remember exactly when, but
Mm-hmm.
it was around that time when lots of issues started cropping up because the set of all sets did not contain itself.
Right. Okay,
Uh,
that's
those issues are currently outside of the scope of today's topic, so I'll not be glossing over them today.
all right.
Kurt Gödel's reckoning. Now, Kurt Gödel is a French mathematician, uh, and who was born in approximately 1906, 1907, around that time. And he was not a believer of set theory. He didn't think,
Right.
he didn't like, you know how the 1900s work. Every
Yeah.
mathematician's job was on the line every time they made a discovery.
Yeah.
Uh, so it's
Same
kind of like the
issues.
discovery of I, the square root of -1. It's like the same thing again. The
Mm-hmm.
world of mathematics at the time was split into those who favored set theory, and George Cantor along with it, and those who called set theory pointless, malfeasant, and all.
Right.
Kurt Gödel was one of them. So, so what can happen is, for the limitations of math, because math does
Mm-hmm.
have limitations. They didn't know it yet. This is like 1900s. They thought everything could be proven, no matter how long it takes.
I
There is a statement which can be proven.
I still think everything can be proven using math. Personally speaking.
Yeah, yeah. I mean, it makes sense. Like a bit of algebraic manipulation here and there. Like math is meant to be like
That math is meant to prove everything.
a
That's
study
what
of
it's
like
supposed to do.
a study of description, like a study of to describe everything you have.
Yes, that's the whole point of maths.
Exactly. So it would make sense if you could mathematically prove everything.
Yes,
Except, as we're about to find out, you can't. So
obviously.
so as we've established earlier, set theory is can be used to represent mathematical proofs and true statements, like the axioms. Because the set theory can represent axioms, you can automatically represent anything which comes from the axioms. It's just a combination of them,
Mm-hmm.
right? So so theoretically, if you can prove a self-referential statement in set theory, it proves that mathematics is incomplete.
Oh,
I
I
want
didn't
you to,
get this part.
yeah, I want you to try think on it and understand what I mean by that.
Yeah.
The key here is self-referential.
Mm-hmm. Not if there is a self-referential statement. Okay, so let's say A equals A. That's a self. Okay, no, wait.
That's not a self-referential statement. That's just a
Yeah.
statement.
Okay, I didn't get it. Can you elaborate?
Yeah, sure. So a self-referential statement is a statement which refers to itself.
Such
So
as?
in the English language, in many other languages, it's really easy to come up with self-referential statements. I can come up with one right now. But in mathematics,
Please.
it's a lot harder. An example of a self-referential statement in English would be, this statement is false. Because,
Ah,
yeah, that's a self-referential statement. Now, that kind of,
this,
what, because if it's true, it's false. And if it's false, then it has to be true. So you're in a cycle, effectively.
right, yeah.
So if you can arise at a contradiction based on a self-referential statement, then you've run into an error. Then the set of axioms you're using either isn't complete, or mathematics is incomplete.
Yeah, that makes
Okay.
sense.
So Gödel's incompleteness theorem. I'll quote this here. In a formal axiomatic system that is consistent and can express basic arithmetic, there exist true mathematical statements which cannot be proven or disproven within that system. Kurt Gödel, 1931. This happened at the age of 25, I believe.
Wait, he said this at like the age of 25?
Yeah,
Interesting.
that's
Most
really
people are trying to get a job at 25.
yeah. Well, he's a mathematician. What do you expect?
Valid.
So try. I want you to try to summarize this the best as possible.
In normal humane English, you mean?
Yeah, not 1930s English.
In any formal axiomatic system. All right, yeah. So basically, all things that are true, any mathematical statement that is true, yeah, is based off the fundamental equations we talked about, such as a equals a and a
Yeah.
minus a equals 0, equations like these. I think that's what this means.
Uh, you're. I think you're about like 60% there. Not quite. You express half a bit. But here's the thing. Okay, there are statements in mathematics which simply cannot be proved. You don't know if
Well,
they're
are
true
they
or
true?
not. So it's not like the square root of 2. We're well past that. It's like we're talk because for one, the Riemann hypothesis could be one.
What's the Riemann hypothesis?
The Riemann hypothesis is uh, the conjecture relating to prime numbers. And it relates to something about the occurrence of the infinite number of twin primes.
Do you expect me to understand a word you just said? You have like very high expectations from me.
I will explain. So basically, a twin prime twin primes are two numbers which are back to back. For example, which are at most one number apart, like 41 and 43. These two are twin primes because they're only one number apart and they're both prime.
Right, yeah.
The Riemann hypothesis, I'm pretty sure, at least I'm not 100% sure, says that there are an infinite number of twin primes and you have to prove it.
Can you prove it?
We don't know.
No, can we prove it like as humanity? Is it provable?
That also we don't know.
Right, so it hasn't been proven yet. Is it true?
That's the whole point of proving it.
So we don't know whether it's true or not.
We don't know whether it's true or not. We do know there are an infinite number of primes that was developed by Euclid.
Oh, I thought Euclid was a geometry guy.
Euclid is a geometry guy, except he also did a bit of prime number math.
Oh, interesting.
Yeah, but we're going too far into the past. Let's come back to a bit less into the past.
I'm back.
Yeah. So Gödel's proof, the crux of Gödel's proof is self-reference. So what he did to prove these mathematical statements is that he gave each operation it's like its own value. Like for example, say ad, addition, like addition, he gave it a certain Gödel number. Subtraction, he gave it a
Mhm.
different Gödel number. Maybe something like, classic set symbols like intersection, union is a part of.
Yes, but however, it would be a little better if you could elaborate on them, like give a basic brief.
Yeah. So let's take two sets, A and B. Hmm?
Mm-hmm.
Now set now it's kind of like I'm gonna relate this a bit to computer science. So now if there
Mm-hmm.
are elements in set A and set B, it's referred to as A intersection B, and A union B refers to everything in A and everything in B.
Right.
Nothing
So
left out.
I think I got the basic point. So if I tell you to get like eggs and milk, then you
Kind of,
have to get like both of them.
yeah, kind of like that.
That's union. That's union. If I tell you to get eggs or milk and you get at least one of them, then that's like
No,
uh
no, 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 no.
no.
Eggs and milk in this case would be intersection, and eggs or milk would be union.
Right. Yeah. I got confused. Yeah, that's what I meant.
Yeah. So what he did was, uh, sir he kept he constructed a statement using Gödel numbers, which created a self-referential statement, which said this statement is unprovable
Mhm.
because if the
Right.
statement is false, hmm, the, then it would lead to a contradiction, and if it
Can
was.
you repeat that? I think I zoned out.
Yeah. So what basically Gödel's statement is for the first incompleteness theorem, there are three of them
Mm-hmm.
actually. Today's topic only encompasses one of them. So
Right.
it says that his unprovable statement is this statement is unprovable in math, and he managed to do it with sets and Gödel numbers.
Right.
So how these Gödel numbers, and now I need you to understand that these Gödel numbers are not like separate identities. They encode information about the axiomatic system of maths within the axiomatic system of maths because you're using numbers to represent them. Did you get that?
Mm-hmm. Yes.
So using this, he is able to create a self-referential statement, which allowed him to basically say this statement is unprovable. So
Hello. It's your voice.
yeah, I'm there. I'm there. So using this,
I
he
think your
was
voice. Yeah.
so using this he was able to.
Continue.
So using this, wait, 3, 2, 1, go. So using this, he was able to prove that statements in mathematics were unprovable. They cannot be proved. Now,
Mhm.
if you want to like if you want to get like better grips to Gödel's incompleteness theorem, because I just gave a very very brief outline of it. Uh, if you're interested, you can access this website and you can read through it. It's a very interesting read.
Can you share the link in the meet, please?
Yeah, sure. I'll put it in chat. Uh,
We can do that later. Just let's go on with the session for now. Yeah.
yeah, that's it. So
Oh, right.
to summarize what happened today, we discussed about Cantor's set theory and how it was used to represent mathematical axioms and proof statements, and then how Kurt Gödel, a French mathematician, completely came over and destroyed uh, Cantor's set theory to the core because it proved that it basically said for a bunch of mathematicians who have devoted their lives to some problems, hey, this might not be provable and your life's work is basically wasted.
Okay.
But however, it did create new things to do. For example, to check, now there are mathematicians out there who are checking if certain problems are provable. Instead of trying to prove them, They're just trying to see if it's provable or not using Gödel's theorems.
Right. So that has like a new dimension. So you can
Yeah,
use one thing to prove it, and then you can use one thing to figure out whether it's provable or not before.
yeah. So it's like the old saying, when some doors close, the new doors open. I don't
I
think
don't see how that's related, but sure.
I don't think I got the saying right either. Yeah, that's it.
All right. Well, thank you for sharing the topic with us, Suhas. This was a very productive session.